So this one gives you the result. This asks you if you had integral cosine to the n. Am I looking at the right thing? Yes. Yeah, x. Thank you. Prove that this equals that. They give you what it should equal. And that looks like, you can kind of see it, UV kind of stuff going on, right? That's got the UV part plus the integral part. So it looks like somebody did something by parts. What could we do by parts here, really?
Make cosine of x u.
All right, so let's see. So if I make, in fact, you kind of can get the idea from the answer a bit.
Just go through the integral.
So maybe there would be something else there. So let's see. So if I let u equal cosine, and what's d? Well, I got all kinds of stuff going on. So it's a little bit easier if I write this like this. Because that's really what cosine nx means, right? So how do I do something that looks like something inside of a power? The n goes down. Good. Negative sign. Okay, we know so far. Now look at the supposed answer. Can you see that? Sitting there. Almost, right? Just missing that 1 over n piece, but we're almost there. Well, this is telling me something kind of. So what would dv be? So b would be. Okay. Neat. So this will be u v minus integral v du. Did somebody else just come in? Oh my gosh. So uv minus integral of v du. And look at du. That's a quick check. You know that the du piece is going to be involved in the next integration step. You kind of with me? So if du itself is disgusting, not always, but most likely we've done something wrong. And this is not going to look like what they have, is it? So, because they gave me what this should become, I can use that as kind of a target, and we've missed our target. Right, so I mean, because this would become uv is just going to be x cosine nx minus the integral of v du would be x times all this mess, and that is just, I know, right? I left out my poor little d. Kind of with me?
Yeah.
So I want to go back and do u and dv the other way. Right, so this is the kind of thing that could happen even on one that's not as weird as this. Yeah, so if I want, now be careful, dv, let's see which way I want to go with this. All right. Yeah, I guess we really only have one thing we can do here. Oh, maybe I should have kept going with the other thing. Real quick, I want to tell you. Today we're going to learn some very simple ways to handle this kind of integral. If it's squared or fourth power or something, we're actually going to use a very basic trig identity. to work with it. So we're going to get something better than this little reduction formula to use on this. But yeah, the only other possible thing I could do would be kind of silly. I'd have to call this whole thing dv, which is my original problem anyway, right? So I guess I should have had more faith. We have to do it the other way that I've already erased. So if we say u is this, like we did, then du is n, oops.
And cosine s times negative sine x.
All right. So then if I say dv is dx, then d is x. So we get x cosine nx minus integral x times, so I get x n cosine n minus 1x. Make this plus because it's a negative. Is that cool? That's disgusting. Oh, I forgot my dx. Little dude. So let me know if everything looks all right.
X cosine n is equal to n minus 1.
Say again? Yeah. This is
On your left.
so uv minus the integral of v du, and this is not a minus anymore because that's a negative, so that came out made a plus. Is that cool?
Could you change u as cosine to n minus 1x, and then dv would be cosine x dx?
So if we split this up, because this does not, I really don't have a lot of faith in this. And this is actually closer to what we do. Because let me give you a specific example real quick, just to kind of cut to the chase here. If I had this, if we like n3, if I had this, why would u sub not necessarily work? What's kind of wrong with this? How do I say this? If I had this, I could break this up as cosine x times cosine squared x. Now, what good does that do me? Oh, I see what they're trying to do. The general form of this looks disgusting. So the actual practical application is much simpler. Why is this any good at all? What good does this do me? Yes, cosine squared. What's the derivative of? Sine. So if I could find a sine in here somewhere, I can make u equal sine, and du would be cosine, and everything would be great. And cosine squared, of course, is related to sine squared. Yeah, so this will be integral cosine x times 1 minus sine squared. So then I can say u equals sine x, du equals cosine x, and that's completely doable. You with me? All right, so it kind of makes sense then that what they want me to do here is something related to what we would do with a nuts and bolts problem, which is to break up this thing here. What's weird to me? Let's see. So does that sort of make sense by itself? So you do have 3 cosines to play around with. I use one of them just to sit there, and the other ones are right in terms of sine, so then I have a u and a du in my integral. Right? So that would actually just become a straight up u sub. It's kind of silly. So here, we could break this up like this. Actually, let me do this. Let's see if that does any good. And see, now we can think about it the same way. Still won't do what I wanted to do. So if I make this n minus 1, so now this is totally cosine n. If I put these back together, these are now n cosines. Okay. I don't have the most faith in this, but let's see. So if I let u equal, so if I want to do this by parts, and because of this problem giving me what this result's supposed to look like, I can kind of play off of that. So the first part of the answer is supposed to look like 1 over n cosine n minus 1 sine x, right? Yeah, cool. Blah, 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 blah. Okay. So then I might be tempted to say, let u equal to cosine. Let's see, does it really matter? So if u was cosine, du would be sine. dv would have to be this thing, which is kind of gross, which is actually remarkably gross. So we can't do that. I can't let my dv be this piece, because it's the part that I'm kind of having trouble integrating in the first place. So I pretty much would have to let u equal to cosine n minus 1x. So then what's du? Whew. Okay. And then dv would be dv would be cosine x dx. And then v would equal sine x. So then we get uv, which would be cosine n minus 1 x times sine x minus the integral of v du. All that mess there. So it'd be plus because of the negative sign again. Still not. I'll have to figure that out.
You can't replace one of those cosines with
Let's be overthinking this thing. All right, let's. So let me work on this, and I'll try to give you what they want. The actual practical application of this problem is very simple. Somewhere I'm just overthinking what I want to break this up between, because this doesn't look like it's going to go anywhere nice anytime soon. v du would actually be sine squared. That looks disgusting. Yeah, that's v du. I don't have a lot of faith in that either. Yeah, I don't like that. Yeah, that's gross. All right, so let me think about that. There's something about breaking that up to begin with in the right way. Right, all right, I gotta think about it. So I'm not gonna waste any more time in class here for that. Let me think about that.
Is the reduction method going to be on the test?
No. So, when I was looking through the homework real quick, these kind of proof problems, normally you can use the result to kind of give you guidance on what to choose. You know, the u and the v you want to choose. I'm not sure here if this problem is several iterations long on this or not, but yeah, okay, so I'm not going to... I kind of see, okay, I see. Well, all right, so let me work on that. So reduction formula is not something you're going to have to memorize. Today we're going to talk about what to do if I have stuff like sine squared x, cosine cubed x, that kind of integral. All right, so I'm not a huge fan of memorizing a lot of formulas anyway. I'm much bigger fan of knowing the process to apply to something instead of just trying to memorize something. And I sort of have given you guys a little bit of a hint as to what to try on these kind of problems here.
Yeah.
Yeah, so whichever one I have an odd number of seems to be the one to pick on here. So if I make this cosine squared cosine, then you just got to be really careful about how you pick your u. And what to do to make them all have the same trig function in them. So what do I mean by that? I mean, if I let pretty much u has to be what? Considering what's kind of free. So both of these, I wouldn't call either one of these free because they're both in a squared function, right? So the derivatives, their integrals would be gross. Which was the freest?
Cosine.
This dude we just plucked off, right? We just shucked off a cosine. That's right, I used to call it shuck. Shuck off a cosine for that dude. So he's what I want du to be. So obviously I would want u to be what? If I want du to be cosine, what do I want u to be? Sine. So then I need to write this in terms of,
Sine.
which I can totally do because it's directly related to sine squared, right? So the practical application of what that's trying to get at is very direct. Memorizing formula sometimes makes it really disgusting looking when actually the actual nuts and bolts of how to do this. If I let u equal sine, du is cosine, then this guy is not covered, but if I rewrite him, so u is sine, but I can rewrite him as 1 minus sine squared, so this will be 1 minus u squared. And what's this here? Du, so that's beautiful. So I have this collection of powers of sine and powers of cosine. That's the general way to try to attack it. If one of them has an odd power, you shuck one of those things off, and then you can attack it with identities like this. Does that make sense? Yeah. Identities come in to help you out so that you have the thing you let u equal so you can replace it with it. Okay, maybe. So a really good question would be, and just to finish this out real quick, what do we get? U squared minus u4. What do we get here?
1/3.
Good. U cubed through 3 minus u5 over 5 plus c, and what was u? Sine. So I get sine cubed over 3 minus sine fifth over 5 plus c. And this is actually a really relatively quick check. Well, not totally quick, but anyway, quick enough to take the derivative of this and make sure that it actually comes out to be that. So those problems are really kind of nice. The quickest way to make it not nice is to take exactly the first thing I said, which was find the one that's odd and shuck, well, what if neither one of them's odd? That's a really good question. What the hell do you do then? So somebody help me out. I showed you last time that the thing I put up on the website now, the trig identities, and it's got that black line, so everything above that black line, I'm going to assume that you know. Below the black line, I don't hold you accountable for, so you can know it or not know it. Somebody remember what these two things are? This one's the nice one. 2 sine cosine, 11. And it's really related to sine of theta plus theta. Remember that sine? I don't know if you guys, real quick little lesson. If I have sine of a plus b versus cosine of a plus b, when I teach this, I call cosine the jackass function. Why do I do that? Because cosine is the guy that says, me first, and u y out plus will screw you. Now I'm going to make it a minus. So cosine is like the jerk function. That's how I remember this. So cosine of a sum is this. Sine is like, we'll both go at the same time, sine and cosine together. And you want plus, I'll keep it a plus. And he's either the nice guy or whatever you want to call him. So sine B, cosine A. Right? So if you ever need, I don't know, if you know that, great. If you need some help remembering it, that's how I remember it. Cosine's a jackass, B first, change your sign, nah. Right? So this is minus, if this is minus, cosine says screw you. But that's exactly where these come from. Sine, if these are the same, I get sine theta, cosine theta, sine theta, so I get 2 sine theta, cosine theta. Whereas these are the same, I actually get directly, I get cosine squared theta minus sine squared theta, but then of course you can rewrite that. Cosine squared is 1 minus sine squared, so 1 minus 2 sine squared. Or sine squared is 1 minus cosine squared And negative comes, I get 2 cosine squared. Okay, my God. This is a long ass explanation. So now if I have a cosine squared in my integral, I can use the identity. Now why? Now in terms of integrals, why is this function so much better than that function? Derivatives of squared functions are easy because it's just chain rule, right? Is there an integral chain rule? No, there really isn't. So it's so much easier to handle just a doubled input. That's not a big deal at all, right? What's the integral of cosine 2 theta? Careful, that's the derivative. What's the integral of cosine 2 theta?
Cosine of 2 theta over 2.
Careful. Integrate cosine. Sine 2 theta
Over 2.
over 2, because you want to kill the 2 that would come out, right? So when you integrate, you got to think about killing things that would normally come out when you take the derivative. You could do u sub there. Oh, please, dear God, you don't need to do u sub there. It's the same thing as like, what's the integral of e to the 5x dx?
E to the 5.
Because you want to kill the 5 that would come down, right? And actually, that's why integral of x dx is what it is, too. It's x squared, but you got to do over 2 to kill the 2 that would come down, right? That's one of the most basic little ideas of integration, is you're thinking backwards all the time. So if you take the derivative, there 2 would be there. Let me put over 2 so it kills it, because I don't want a 2 there, right? So coming back up to this. If I had got that one all done. If I just had this, I could rewrite it as 1 minus sine squared. I'm still screwed. So of course, cosine squared theta equals what? If you solve for cosine squared, what do you get? 1 plus cosine 2 theta all over 2. So I can replace this with that form, which on first glance is like, well, that's worse. There's more stuff in it. There's no squared functions. If it's not squared, it's much easier to integrate. So this would become the integral of 1/2 plus cosine 2x over 2. Or you can keep it together if you want to, whatever. And then what do you get when you integrate that? Yeah, x over 2. What's the integral of cosine?
Negative
Sine. Sine. Over 4, good. The 2's there, but you need another 2 to kill the 2 that would come down. You guys semi with me on that. Some of you guys are looking like you want to hurt me. So again, when you integrate some function of twice that thing, twice the input, right, you basically get the integral f divided by 2, because you got to kill that 2 that would come out if you took the derivative, right? That chain rule piece. So that would be, the integral of that would be sine 2x over 2. It's already over 2, so now it's over 4. Not a big deal. Or maybe. So if there's an odd power, awesome. It's got an extra cosine or an extra sine that you can shuck off, or you can pick off, or whatever verb you want to use there, that you can use as in u sub. If everything's even, you have to use these kind of things. So if I have sine squared theta, that would equal 1 minus cosine 2 theta over 2, right? I don't know if you guys remember that. The plus and the minus in those. So that's the trick. That's how I memorize stuff, is I only memorize this, and then I can build this, and then I can build these. I don't have that much space left for memorization. All right. So before I go too much deeper into that, I've sort of already launched into the lecture for today. Were there any other questions left over from the by-part stuff?
30.
Let's see what happens. Okay. So 30's got an arc tangent in there. Okay. So here, pretty much, I only have one function that I can play with for by parts, right? So I can't let dv be this because then I'd be right back to the integral that I'm working with. So I'm pretty much got my hands tied. I gotta let u equal to this piece. So then you gotta remember what the derivative of the reciprocal of the inverse tangent is.
Negative 1 over x squared.
So in general, so if I have a tangent of x, its derivative is negative 1 over
X squared plus 1.
x squared plus 1. So in this case, what am I have to be careful about?
Dx.
The 1 over x. Good. So there's two things you got to be careful about. I want you to really be careful about this. And one thing you have to get used to for mathematics is to realize that a lot of math is about the form of things. So the tangent of something is negative 1 over x squared plus 1 times the derivative of that something. Now here, of course, I got an x, so it wouldn't really matter. But if I had tangent of u, right, and I don't mean tangent, I mean inverse tangent. This would be negative 1 over u squared plus 1, right, times u prime for the derivative. So whatever the hell's there goes there, and then its derivative has to be multiplied. That's the chain rule piece. So when you do this, the derivative of tangent is negative 1 over the thing squared, and what's the thing? 1 over x. Good. Times the derivative of 1 over x, which is, careful, that's the integral. What's the derivative?
Negative 1.
Negative 1 over x squared. I like it. Dx. That'll just be there forever now. All right. That looks really disgusting. What's really kind of nice about that? Do you notice something nice about the functional part and its chain rule piece? What they do together? Aw. If you multiply through,
Turns positive.
do you that it becomes positive? It's really nice. But then this is 1 over x squared times x squared is 1. Do you guys see? I'm just multiplying those together, right? And of course, plus x squared. That was really nice. Those two together made something that looked a lot better. Okay, maybe. Okay, cool. So now let's piece it back together. Now, I still have to identify, of course, dv is going to be dx, so then v is x. Okay, that part was nice and easy. So what do I end up with here now? I get the integral, and I'm not even going to worry about these. Inverse tangent, oh, sorry, what did I do? So I got my uv minus integral v du. So I got uv, and that's going to be from 1 to root 3. Minus the integral of what happens in there? Yeah, minus x over,
1 plus x squared.
or as v du.
Wouldn't it be plus?
Why?
Because it's going to be a negative.
Which piece is negative?
The u, or the v times v.
So it's v du. So v du. Cool. And what's really, really beautiful about that integral that we just created, besides Jeff forgetting those again? What's really, really nice about this integral? What method would you use? U sub. Just straight up U sub. Which when you first learned it was disgusting, and now it's like, oh, thank God I can just use U sub, right? I don't know if you're really there yet or not. If you do enough by parts, you'll start to really love U sub. You guys see that? The U, the V, du fill each other in, and that is this guy's derivative, basically, minus a constant. Who cares about constants? I can put them wherever I need them. So this piece you can throw in the root 3 and do your stuff. So it'll be root 3 inverse tangent of 1 over root 3, which is a angle you should know. Yes, ma'am.
The derivative of arctan x is just like 1 over 1 plus x squared, not minus 1. And the du,
Yeah, okay.
it's just 1 at the time.
Just a positive here?
Yeah.
Okay. Tell me these things earlier. So then, I don't make my students memorize these, so I don't memorize them either. So it's going off what somebody said.
It should be
So,
It's
that'd be -1, okay. I'm with you. That's the only thing that changes there, and then this would be a plus there, right? Yeah, cool. So, you know, what's that angle there? You guys know? 5 or 6? Everybody agree? So real quick, what I do is I don't memorize these. I just remember tangent, sine over cosine. So where's sine smaller than cosine when it's close to the x-axis? So 5 or 6 makes sense. 30 degrees. Do you guys see that? Yeah. This would be the tangent of an angle equals this. And tangent sine over cosine. So sine is smaller than cosine at 30 degrees, 5 or 6. Closer to the x-axis because cosine likes x. So this would be root 3 times pi over 6. I like that. Then you throw a 1 in there, minus inverse tangent of 1. And of course that would be pi over 4. I love it. So we get root 3, pi root 3 over 6 minus pi over 4. That's for that little uv piece. And now we still have to do this integral. And I'll leave something for you guys to do for homework. This should be a relatively easy u sub integral to do. You can finish that out. Be really careful. I definitely will give you values that you should be able to do these trig functions for. If I see decimals all over the place, it's no good. I only want you to use decimals if I ask you what's sine of 11.8 degrees. Right? That's not an angle you should memorize. So it's okay to use decimal approximation there. But something like this, I shouldn't see a decimal approximation. I should see what the actual answer is. Okay, maybe. So anytime I give you on a test something I don't expect you to have memorized, so I don't make my students memorize the inverse trig integral derivatives. I don't. So I would supply them to you. Right. So you got everybody understands you're not done. You got to finish it up for homework. So anything else from section 7.1, the by parts section? Okay. All right. So let me get back into this kind of problem here. Let me go ahead and give you the handout for this. I think a few of you guys got the handout last time because it was in the back of something else I did. Huh? Yeah, I could have sworn.
The bottom is right.
Oh, that's right. I'm not going to do that. put this on the overhead. If you didn't get a copy, I'll put it up on the website so you can go there and grab one. I'm really amazed at how many people are here. What's that? Oh, so you had one with the back.
Yeah.
So if you had one with 7.2 on the back, there were just a few of you guys that had that. Coolness. Anybody else had that? If your 7.1 handout had 7.2 on the back? My printer worked for a couple of those, and then it... So I'm not going to... Oh, thank you. Huh? Oh, you have one? Oh, cool. Oh, sweet. All right. Look at that. Stuff happening. You have that? Okay. So just a few of you guys in the middle there. So real quick, I just want to show you what's on here, especially if you can't see it. Seven two to me, you always have the option of memorizing stuff or just seeing why certain things make sense. And I am a big proponent for seeing why things make sense. Less memorization. Right? I think one of you guys even put on the survey that you hate all the memorization that you have to do. And my suggestion to you is you don't have to do all that memorization. There are certain things you have to memorize, that's for damn sure. But for trig identity stuff, I memorize certain key things and then build off of it. Right? Like the sine squared cosine squared equals 1. Divide by sine squared, you get another trig identity and so forth. Those kind of things. Let's see, which one are you? I think it's this one. Yes, great. So real quick, just want to show you what's on this. I tried to boil it down to the really important parts. Okay, so this is what I was saying earlier. Whoa, neat. All right, thanks. So if n is odd, so if you have this integral of these mixtures of powers of sine and cosine, if n is odd, I could split off the factor of cosine in this case like we did just a second ago, and that would be part of my du. Right? If m is odd, I could split off factor of sine and do the same kind of thing exactly. Right? Not a big deal. And if they're both even, so I can't, so if they're both odd, you just pick one to do this kind of thing too. If they're both even, that's the one where you have to use these identities that we talked about earlier. I showed you where those came from. So what I want you guys to do is to attempt a couple of these. Let me give you, before we go to these, all right, I'm going to give you a few to try from here, these kind. We make some up. Actually, let me just pull some out of the book here. Okay. So let me do some classic ones here. Alright, so based off of this, try doing integral, one. Yeah, let's just do a straight up one. Sine x cosine. Oops. Let's try to do that one. Can you guys see that? Sine x cosine to the fifth. Sort of evil in a way, but let me just let you guys think about it. And then let's try. Bless you. Try that. One more too. 6. All right, so call me over if you need some help. Real quick, just make sure I was on the right track with number 1. Do you guys see what's really nice about number 1? Yeah, you could pick which. They're both odd powers, right? Okay. Yes. So I could shuck a cosine off, but this is not enough. Let me see how I want to say this. If this was like sine squared, then I could actually use the identity directly. Otherwise, I've got to bring like a square root and all that stuff in. But it's much better to use this as my du piece. It's already kind of like by itself. So if I let u equal cosine, du is negative sine. So I just have to introduce a negative. So that one you actually don't have to mess with it at all. It's already kind of got a spare part by itself already floating around. So you can use it as your du. Yeah, I just wanted to give in a bit. Give you guys the first step there. If you're having some trouble with that. Yeah, hello. You're fine. Yeah, this one, there you go. Yeah. yeah, so you shucked off the sine. I love it. Yeah, good. Oh, I see, you rewrote it. Yeah, that's valid. Yeah, you can do that. Yeah. I'm not going to necessarily teach that. But if you notice it, that's okay. But see, this is only 4 cosines, that's 5. So yeah, so that's what kind of messes up going that way. Okay. So then, if you want to use cosine, but then what do you do with the cosine 4x? Not everything's in terms of u yet. So you can't, when you're doing u sub, you can't go forward unless you got everything in there covered. Meaning it goes from being put on an x to being no. You do it the other way. You let u equal cosine. Because there would be some cosine's derivative is in there. Yeah, that's fine. If you're off by constant, that means you're on the right track. You're fine. You can always put whatever constant you need to in there. Just balance it out. I know you can see it all. All right, guys, so real quick on the first one. Let's make sure we get the first one down. So there's several things I want you to realize. When there's several powers of sine and cosine, the nice thing is if you just take one of those two off, and we normally try to go for the odd one, they're both odd, you can pick one. Because then you have a du, and then u is very obvious what to make. So whenever you have one that's already to a first power, that's what you want du to be. It's already there for you. And then it almost doesn't matter what the other power is. Do you see what I'm saying? I don't care what the other power is. I'm going to let u equal cosine because sine is free. Sine x dx is by du. So then u must have been something related to cosine, right? So if I let u be cosine, then du negative sine, but the negative I don't care about because I can just put a negative on the inside and the outside to balance it out, right? So then this is, what is that I just circled? Du, that's du, and then this can be written as u to the fifth, and then that's nice and easy, right? How do you integrate u to the fifth? And then just put the u back in, right?
So we're not using the rule right now?
Totally are. We totally are. But the nice thing is, this is already by itself. Right? So, they're both odd powers. So I could either shuck off a cosine or I could shuck off a sine. Sine's already there by itself. So I would choose that. It's already kind of set up for me. Right? And think about this too. If the power is below c, so if it's a first power, I can't really use that cosine squared plus sine squared equals 1. I can't use that really nicely. I have to introduce square roots. You could do it that way, but I don't want to. So then this would be negative cosine 6x over 6 plus c. So, just to make sure everybody does this one the right first step, you've only got sine to deal with. It's only even power, right? If it was a cube, what would you do? Yeah, take a sine off. Right, so that would be your du. So when you're to be cosine, so you have to rewrite the sine squared you would leave as 1 minus cosine squared. But this is an even power, which people kind of don't like, but you just got to remember the identity. Sine squared x is...
1/2.
Okay, 1/2.
Yeah, 1 cosine of x.
Okay. 1 minus, remember the sine is minus, cosine is plus. 1 minus,
Cosine of x.
good. And the biggest mistake I see is people think it's sine just because it started off as sine, but all that squared stuff is related to cosine of a double angle. All right, and that should be relatively easy to finish out. And of course, what told me to do that? All the powers of trig functions. I know it's only sine, but just all the powers of all the trig functions in there are even. Shit, I've got to use that. There's no other choice. I can't take the odd guy off to make him du. I can't. There is no odd guy I can take off. So I have to use that. What would really suck if I would have made that a sine to the fourth? Then you would have had this whole thing squared. Yummy. So that could happen to you. We basically did this one earlier, right? The only difference was it was when I had plus, because it was a sine squared that I had in there. I mean, a cosine squared that I had in there. So what would that integral be? X over 2. Sine 2x over 4 plus c. Oh, it's like a square. It's not. Oh, that so desperately sucks. If your handwriting is anywhere near as bad as mine, maybe even worse, I feel really sorry for you if it's worse. Coefficient of 2 becoming a square, that happens, and then it really just throws everything way off. So be careful about if it's a coefficient of 2 or a power of 2. Everything changes. So what the hell do you do with number 3? What sucks about that one? Yeah, tangent sucks, because all we know right now is cosine and sine, powers of those. So of course tangent has...
Can we do sine over cosine?
Good, so tangent cubed would be sine cubed over cosine cubed. So how many cosines cancel? So then you get cosine cubed. Just trying to do the 3 there, sorry. So now you get to pick. They're both odd. So now you get to pick which one to shuck one off of, right? Since the derivative of sine is cosine, I tend to like to shuck off a cosine. Let that be du. Whatever you're going to shuck off is going to go with the dx and become du, right? So if I take one of the cosines off, this is going to be my du. So I want to let u equal sine, which means I need this written in terms of 1 minus in terms of sine, so then I can finish my substitution. You with me? So another big mistake I see is people leave this cosine squared x and then they got u stuff here. That make a damn bit of sense. You don't want x's and u's in the same. You got to cover all your x stuff with u. It's a strange sense. So cosine squared 1 minus sine squared, sine cubed, cosine x dx. So if you let u equal sine, because that's all over the place, this is sitting there wanting to be your du. So you let u equal something that will lead you to this du. I'm right so small. So now I get integral of 1 minus
U squared.
u squared times u cubed du. Coolness. And then that's easy, right? That's polynomial in nature. So those integrals, you just, pray for those kind of integrals. So then you get,
U to the 4 divided by
good, and u was
4. Sine.
sine. So it might as well sine 4 over 4 minus sine 6 over 6 plus c. Coolness. What's that? Now, real quick word. I was talking to a few of you guys. Some of you guys saw where you didn't even have to do this u sub, and that happens in a few integrals. If you could just kind of see the derivative in there of the function, you can sometimes skip this u sub step, and there's not a damn thing wrong. As long as I see all the stuff before that, I'm cool with you going from there to there. If you can't see it, it's no problem. You got u sub to do that. That's awesome. Nothing wrong with that either. So I don't like to teach. It's better for you to kind of see that than for me to try to force you to see that. You've always got this process if you need it for u sub. So when you see one of these integrals, and I got sines and cosines, powers of them, what do you look for? Yeah, you look for one of them to have what kind of power? All right, so if at least one of them has an odd power, you go, okay. Then you can just take one of them off. Whatever you took off, that's your du, so your u is going to be the other dude. Right? And then it's relatively simple after that. You just got to let it be simple. And of course, if neither one of them's odd, you got to use that identity. And that's one of the ones I'm going to make you memorize. Okay. Cool. So the only other part here is if you have combinations of tangents and secants, and of course that's because they have their identity, much like cosine and sine does. So it's very similar to cosine and sine. If n is even, now this gets a little bit more interesting because what's the derivative of tangent? Secant squared. What's the derivative of secant? Secant tangent. All right. So let's see. Let's try a couple of these. So let's see. If let's make one of each of these kinds, each of these flavors. So if n is even, that means that secant is to an even power. So let's make one up like that. So I got the integral of tangent 3x secant squared x. So what does it tell me to do, and why does it make sense? This is almost too easy, but so for cosine and sine, if I take a sine off and put it with dx, I want u to be. Well, you're thinking ahead, but for cosine and sine, if I took sine and put it with dx, sine x dx, that's my du. I would want u to be cosine, right? And the negative I worry about later, right? So since the derivative of tangent is secant squared, that's why this is saying if n is even, I have an even number of secants, I can take two of them off. So now if I have secant squared dx, that's what's going to be my du. What would you have to be? Tangent. Tangent's what would lead to this derivative, right? Same idea as cosine and sine, but of course their relationships are different. So this is why I don't like to memorize too much stuff. I just memorize the idea. Whatever I take off, I want it to be the du for something. And it tells me what u's got to be to make that work. So if n's even, I got at least two of these. That's going to be my du. So u is going to be tangent. So then du is this. So tangent cubed I can write as no. U cubed secant squared dx equals du. I kick so much ass. Yeah, so u to the fourth over 4. And u, of course, was tangent. So I get tangent to the fourth x over 4 plus constant. So that's not bad. Now let's try this a different way, because what's the second option you could do? If m is odd, if the power on the tangent's odd, and that's exactly how I made this problem, right? Sometimes there's a method to my madness. So if we do this problem in a slightly different way, the same problem, let's see if we get the same answer. If we don't, we can throw the whole thing out. So what to say, if m is odd, what can I do? Yeah, split off a factor of secant x tangent x. So if I split that off and put that with dx, what would you have to be to make it secant x tangent x dx? Secant, because that's its derivative. You with me? So you see how this kind of all comes back to the same idea. So if I do take a tangent secant, that would be tangent squared secant, right? If I take a tangent and a secant, and I'm sorry, let me finish this out. There's my tangent secant that I shucked off. Since this was odd, I can take tangent secant off, and now you can see why it's important. To get this to be du, u has to be, again, secant. So if I let u be secant x, du is... Yeah, you guys are like, we just said this, Jeff, stop it. Sorry. And why is it important that this was odd to begin with? If you take one of them off, now it's even, and why is that important? So they use identity, because since my u is secant, I need the stuff inside here to be in terms of secant, so I can actually make the appropriate substitution. So this I can write as what now?
6x minus 1.
Good, minus 1. That's what that piece is, times secant x times this mess. And now let's substitute. Sorry, thank you. I like how everybody's like, just please do it. Just tell me if I'm doing that. Sorry. And now, so u is secant x, so this will be
U squared minus 1.
u squared minus 1 times u times, sort of times, but du, because that's what du is. That's why we shucked it off and put it over there, right? So that could be du. So again, I'm trying to show you, I've given you a handout that actually makes it look like I want you to memorize this stuff, but it's really just the guidelines, and then you make sure why it makes sense. You don't memorize what to do in these situations, but you just see why does it make sense. It's all about whatever you pull off is du, tells you what u is going to be, it tells you what you got to rewrite using identity so that it'll show up. So if this has got to be my du, my u's got to be secant, crap, it's tangent, let me make it into secant. Who had a hand up? I'm sorry. Right over. Yes?
Shouldn't u equal secant x?
Oh, I'm sorry, I keep doing that. Thank you. Yeah, and then the dx comes in, you actually do a derivative. Thank you. So then what do you get here? You get
u
cubed minus u, so that's going to be, careful, you got to do the integral. So maybe we shouldn't do that. Let's not skip any steps. u4 over 4 minus, and then you put back in what u is. Secant 4x over 4 minus secant square x over 2 plus c. Bam. You start to realize this kind of thing happens a lot with power on the trig and the denominator the same. It kind of makes sense because when you take a derivative, it's going to cancel, right? So you kind of expect that to happen. Okay, how do you guys feel about that? I mean, that's just something you just got to do a few just to get it in your head how it kind of flows. Okay, maybe. So let me give you one more of those to try on your own. Let me see if they have any freakiness in here. Oh yeah, so what if they had this evilness here? evil do I want to be? Not too evil. Oh, so for this one, you would so see how there's 4 sequences. So let's split it into 2 sequences. Exactly. So split off 2 of them. Put that with the theta. And that tells you what you can use that. So if you put this with your d theta, this is going to be your. So what's u done? The derivative of tangent theta is my yeah. So now if anything's not in terms of tangent, it's got to be written in terms of tangent. I mean, you could, but it's not going to help you do this interval. So they don't mean use this directly. They mean not the way you're doing it here, but so when there's an even number of sequences, you take 2 of them off to equal this one. So that'll be your DU. And now you know what you're used to. If you put it in all terms of all these powers of tangent, I don't know what the interval of tangent before. So it made my interval worse. Yeah, cool. Yes, we're very close to it. Okay, explain it. Yeah. Okay, good. Yeah. How did you go from here? That's what. And I see what's wrong here. Right there, it's point plus. Otherwise you're fine. That's what I meant by you can see a different way to do it. But that gets a little complicated sometimes, but you can always see how to put that together. You don't have to do the stuff, right?
For you, it doesn't make sense. So like, you'll have a practice.
Oh, here to here. Not like terms. No, these are not like terms. Because it's usually the fourth of the square. Okay. So u squared. This is the original paper. And then you take u squared is. All right, let's do this here. So of course here, this is even, so I can just take a couple of secants off of there. So now this is going to be my du. That's why I took it off of there and put it with the d theta. So that's going to be my du. So then my u has to be tangent. So this guy is the odd man out right now. Right? Can't be covered by the u sub I want to do, so I just replace it with tangent squared plus 1. So that's there. That's been replaced using an identity. That's there. This is going to be my du piece here, right? Okay, so then u is tangent, so I get u squared times u squared plus 1 times du. Sweet. And that integral will eventually be really nice. I like it. So that'll be 5. That'll be 3. Sweet. So this is about the same length as those of you who have discovered a slightly different way to do it without using u sub. There is a slightly different way you can do this. But again, it's really kind of easy to make mistakes going that way, but if you want to do it that way, I love it. Otherwise, you got this way. Now, what's a little bit evil, let me show you an example of a little bit of evilness. Calc 2, you should expect that in the homework there will be a little bit of evilness. Look at this. What's evil about that? The x. What the hell? There's no room for x in any of the rules we discussed. So what method do you have to use here? Integration by parts. Because this is a what? That's a derivative. So that could be my dv. Right? This here is a derivative, right? And this, it could be my u. So it looks like my parts will work. So if u is x, du is dx, then I want to let dv be secant tangent, because then v could be secant. Whew. So then I get, how do I put this back together? uv
minus integral v du.
v du. And now you just got to remember what the hell that is. If only it was secant squared, that'd be awesome, but it's too bad. It's not. All right, so we get x secant x. This guy is a little weird. It's the natural log of, yeah? That's some weird ass stuff. We could prove that by rewriting secant as you could do like 1 over cosine and try to do something with that. Not very simple. That's, for example, they have it on page 475. I don't know, I'm of two minds on this. What's the, so that's the answer to that problem. Somebody know what the integral of tangent is? That keeps coming up every now and again. Yeah, you can say natural log of secant x, or you can say negative natural log of cosine, because of course that's the negative power coming down and flipping that secant over to a cosine. Is that cool? So either one of those two. Okay. So I don't know, I might not put it on the test and maybe just make you come up and ask me if you forget. But you might want to, and what's kind of nice about this is what's the derivative of secant x? Secant tangent. So it sort of gives you, right, remember the integral of secant is ln, you know it's got to be an ln because secant is a reciprocal trig. Ln of tangent plus secant. That's sort of a way maybe to memorize it. But if you forget that kind of thing, if it's on the test, you just come up and ask me. And I'll ask you what you think, and normally you're pretty close. All right, how are we doing so far with that kind of stuff?
Great.
It's not too bad. It's not too bad, right? Relatively not bad. Okay, I want to do one more thing with you guys. Yes, ma'am.
By the time the test comes, can you like make us repeat stuff?
To do what? Sorry.
Make a sheet of things we're supposed to remember.
Right now, the trig identity stuff above the black line is there, and you definitely have to know all the derivatives of your trig functions, right? The inverse, inverse trig functions, I don't normally make people memorize, but if you got to memorize, kick ass. If not, I'll put them up on the test if you need them. Let me think. What else am I missing? Oh, I can't remember now. Basically, if there's something on the test you kind of forgot, you can just come up and ask me, and I'll either say, tell me what you think it is. And normally people are either right and they're just not confident about it, or they're really close. But you definitely have to know your basic trig identities, the upper part of that green handout, and then your basic trig derivatives, right? I'd love it if you should know your integral of sine, cosine, but now I'm throwing on there tangent and secant. It would be really nice to know those integrals, right? But as always, if you forgot something, you just got to ask me, and I'll prod you to see how much you know. What was it I wanted to show you? Oh, before I get too far away from this, just to kind of alleviate my brain, I should have looked for this first. Very often what happens, I don't know if you guys remember this, but you see this all the time. When you're trying to prove something in mathematics, sometimes it takes a little bit of weirdness to get there. And the time it took to actually get to that point was normally a pretty decent amount of time to get to that point where you figured out all the weirdness to do. So the question earlier that I couldn't quite get done on the board, I don't feel so bad anymore because it is a very weird thing you have to do. And I think if we would have just stuck with some stuff we were doing, it would have eventually worked. And the reason they asked you this in the homework, and the reason I was cool with it, is because there's an example of integral sine n. So see what they did and apply it to cosine n, right? So I should have started here, because remember, what did I say? Appreciate the fact that your book right now has examples. Because if you go much further in mathematics, eventually they're not going to have any damn examples. Just theory and then application of theory is on your shoulders. So always look for examples related to something if you're having trouble with the homework. That might be the reason why they felt comfortable asking you this, and that's exactly why they felt comfortable asking you this, because they had this example in there. Cool. So I felt a little better when I saw that. It's like, shit, I can't remember that. This is a little bit of weirdness. Okay.
There's a student solution manual too, but I'm not sure what that covers. I believe it shows the steps for all the things it solves. I'm not sure.
Yeah, the student solutions manual shows the steps for all the odd problems, right? And I think it gives you the answers to the even ones, if I remember correctly. Anybody have the student solutions manual for this book?
I have it, but not with me.
I love you guys. You're all like, no.
It doesn't show that you
Who needs a student solution manual? Or you're like, dude, I had just enough money to get this damn thing shut. All right. I understand that.
Yeah, physics book.
Physics book
$200.
eats up a lot of money.
Yeah,
All right.
$200 book.
So last thing I want to do today is the next section. All right. So the next section, and again, let's see if I have enough of these.
Just one of these. Because all those are the near black lines.
This is 7-3. Yeah. 7-2 just focus on that trig integral stuff. Let's just see how that works. Let me know back there if you run out before it gets there. Oh. Oh, good. I did email somebody.
Tattoos. Cost $5,000. It'll stay there for a while.
All right. This is trig substitution. So it's like U substitution, so forth. It just comes out of left field very often. It doesn't feel like something you should be allowed to do. So let me, before we look too much at this, shoot, I've run out of scrap paper. Before we look too much at this handout, somebody have some scrap paper I could borrow? I've given all my scrap paper away. Rawr. All right, thank you. Okay, so let's do a little motivation behind before we get into all the little specifics here. But you can see the form of this, and that's if that shows up in an integral, it might be something related to sine, because 1 minus sine squared. So constant minus function squared equals that. You kind of with me? And look at the form of this, constant minus function squared. Do you guys kind of see the idea? So if I have constant function plus constant squared, that would be more related to that, right? Function squared plus constant. So okay, so on that level, it's kind of like, sure, Jeff, whatever the hell. But watch this. Let me see. Let's do a simple example here. Now it's U. Right? Yes. Okay. Thanks. Look at that. I got line paper and everything. It's crazy. All right. Let's see. Let's see. A really nice, simple example. Sure. Okay. Now, let's figure out. There's always got to be. It always has to make sense as to why we need to come up with a different way to do something. If I try to do this integral based on what we know so far, what would you try that immediately you can see it doesn't work? Like U sub. Would U sub work on this?
No.
Hell no. U sub won't get me anywhere. I'm missing some stuff here. It's not going to work. By parts. Could you imagine trying to do this by parts? The thing with by parts cannot do that U sub can do is U sub can take the place of something inside another function. By parts cannot. By parts, every part has to relate directly to a function that's in there. You guys see the difference?
Yeah.
So I couldn't let U equal 9 minus x squared, for example, if I wanted to do by parts. So the fact that the square root's in there is remarkably disgusting. Right? So by parts more than likely would not work. Now some trig integral kind of stuff, trig substitution stuff, you can do a different way, and I might try to do some a different way if that shows up. But what kind of tells me that trig sub is a good idea to use here is because the form, under the radical I got constant squared, 3 squared, minus function squared. Right? So what trig identity would that be related to? What trig identity would that be related to?
Sine.
1 minus sine squared equals cosine squared. So now watch this. This is where things get very strange, and this is where students have to remember that if I said U equals x squared or something, you're already cool with the fact that I'm replacing an x function with a U function. So in this case, I'm replacing x functions with angle functions, really, with me. And they happen to have an extra piece. For u sub, I could say sine u equals x squared if I really wanted to. More than likely, it won't get me anywhere. So I can, what is x? I don't know. So why can't it be 3 sine theta? Oh. Sorry. I just written a ton of zeros on there because I was on the keyboard. That's neat. So my handout looks really freaky. So why the hell, where's that 3 coming from? Yeah, because after I square it, I want to be able to take that 9 out of the way. And you kind of see how this kind of comes together? Whatever that number is, the square root of it is what I'm going to put there. Because let's just focus on that piece. What happens to this if I make that substitution? What happens to that part? It becomes square root of 9 minus...
9 sine squared.
Good. Now what can I take out of there?
The 9.
Sort of.
Factor of 9.
Yeah. Square root of 9 is 3. So a 3 can come like that. And what's left inside?
1 minus sine squared.
Oh, sorry. Thinking ahead. Sine squared. And of course, 1 minus sine squared is...
Cosine squared.
And of course, the square root of cosine squared is...
Absolute value.
Alright, and we normally don't worry about absolute value. We'll see why in a bit. Okay? Alright, so how are we doing so far? I mean, so... If you're cool with me replacing x with u stuff, you should be completely fine with me replacing x with theta stuff. And in fact, I can look at sine theta itself as a variable in a way. It's an unknown quantity, so it's a variable. It can vary based on what theta is. So that piece of that integral simplifies to this. That looks a lot more doable, right? But what else do I have in there? I got x squared. What would I put down there? So far I've got, this becomes 3 cosine theta. What do I put here? I love it. The square of that, so 9 sine squared theta. Now what's dx? If x is that, dx is... Careful. Careful. You differentiate.